So thank you all for coming. So I last did one of these discourse lectures in 1994, 31 years ago, on the 25th of February, so nearly 31 years ago to the day. And Dorothy showed me the abstract that I submitted, and this is a very different talk. Okay. What I'm going to do is I'm going to ask whether we've established a standard model of cosmology in the way that particle physics has a standard model of particle physics. And I'm going to do it from a historical perspective, and a personal perspective, sort of my journey in cosmology. So I'll start off with, normally speakers don't advertise their age, but it will turn out that this is relevant to this talk, because what I'm going to do is I'm going to start at the very beginning, or at least close to my beginning. So here is me when I was 3 years old. So this is 1958. And what was cosmology like back in 1958? Well, the big questions were between the Big Bang theory, was the Big Bang theory the correct description of the universe, or the alternative was the steady state theory. And these are two of the leading figures. So Fred Hoyle was a big proponent of the steady state theory of the universe, and George Efstathiou, who was one of the earliest proponents of a Big Bang theory. So back then, cosmology was little more than a branch of the philosophy of science, because there was no data. So you had these big arguments about what cosmology was like. But then there was a paradigm shift, and the paradigm shift came with the discovery of the cosmic microwave background radiation. So this shows Penzias, Arno Penzias and Wilson, who used a radio receiver and detected radiation from the Big Bang. And this radiation has a temperature now of 2.73 Kelvin, so 2.7 degrees above absolute zero. And if we extrapolate back in time, then the universe gets hotter and hotter and hotter as we go back in time. So this, absolutely proved the Big Bang theory, that the universe started off in a hot, dense state. And the other interesting thing about this discovery was that there's been a long-standing problem. The sun has 27% of the sun is helium. The sun's mass is in helium. And you can't form that amount of helium through nuclear fusion processes in the sun. If the universe is hot and dense, in the very early universe, you can form helium through fusion processes. And that calculation, if you do that calculation, then to get the abundance of helium that we observe today, you need a radiation which would have a temperature at the present day of about 2.7 Kelvin. So that was really, conclusive evidence in favor of the hot Big Bang model of the universe. So that's the first of my paradigm shifts, the discovery of the cosmic microwave background radiation and the fact that the universe must have started off in a very hot, dense state. So 1965, so I was 10 years old, and at our home we had the Artemis Children Encyclopedia, if anybody's old enough to ever heard of that. And in this encyclopedia, there were pictures. So this is one of the famous Porter prints of the 200-inch Hale telescope at Mount Palomar in California. And for me, that was inspirational. Okay, you know, this amazing thing that was built and came into operation in 1949, and that was inspired me to do cosmology. What were people going to discover with this amazing machine? And it really is amazing. So this shows you the scale of people. It's the most beautiful telescope in the world. If you ever get an opportunity to visit it, it was designed in the 1930s, so everything is, you know, deco-styled, and it's just beautiful. So, so I was, you know, inspired to do cosmology from when I was 10 years old. And to remind me of why I do cosmology, I have prints of the 200-inch at my office at home and in my office at work. So it's a reminder. Okay, so I wanted to do cosmology and then did the usual stuff of doing physics and so on and so on. And I ended up starting a PhD at the University of Durham. So what do you do? What do you work on? So we knew from the discovery of the cosmic microwave background that the radiation, you know, the universe started off in a hot, dense state. But we didn't know very much about the structure of the universe. And so what I discovered when I was at Durham, I discovered computers. So here is a picture of a computer of around sort of mid-1970s vintage. And in those days, if you wanted to use the computer, you had to wear a suit, go to the computer laboratory, and the way that you interacted with the computer, this is a punch card machine. You sat at the machine and you made little holes in cards. That was your computer program. And then you weren't allowed to touch the computer. You handed the cards to a nice young lady who would load them, feed them into the computer, and then the computer would run whatever it was that you'd instructed the computer to run, and you'd get the output the next day. And that was how it worked. And so what I started working on was the formation of structure in the universe through gravity. So the idea, you know, I mean, this actually goes back to Newton, that if you have a distribution of matter that's nearly uniform, then gravity will make it worse. Okay, so formation of structure under the action of gravity in an expanding universe. So what I'm going to show you is a simulation from that vintage of you know, how structure forms under the action of gravity. So it's done in an expanding universe, but I've scaled out the expansion so that the box size stays the same. Okay? So this is a segment of an infinite universe, and it has periodic boundary conditions, triply periodic boundary conditions, and then we evolve this under the action of gravity. And so here's what happens. Okay, so after the universe is expanded by a factor of 20, you can see that you form nonlinear structures, you form clusters, and so on. And the sort of problems that I was interested in back then were to find scaling solutions. So if you start off with scale-free initial conditions and you run with scale-free expansion history, do you get a scaling solution? In other words, you know, that you can match the structure that you see here at different times through rescaling the length scales. So that was the sort of problem that I was working on. Now, a calculation like this back then took around 3 weeks of computer time on the most powerful computers that I had access to back then, which had less computing power than your mobile phone. Okay? Now, what I've shown you, this little video that I've shown you, I did that a few years ago on a MacBook Air for another talk. I found the old program which worked first go, okay, and then I ran it on a MacBook Air. And it took 30 seconds on a MacBook Air. So that shows you, and that was several years ago. So, I mean, as a graduate student, if you'd given me a MacBook Air back then, I would have ruled the universe. I mean, and just to, follow on from that, how, computer technology has evolved. So this is an example of a simulation done, so this is a group led by one of my former graduate students. This has 300 billion particles. The previous plots that I showed you had 32,000 particles. So this is what you can do now, and you can do that with modeling the gas and the formation of stars and so on. So that's what you can do nowadays. Okay, so back then studying the formation of structure in the universe, but I had no idea, we had no idea back then of what the initial conditions should be, what the starting points were. As I said, we were experimenting with scaling solutions, scale-free initial conditions, but we didn't have a clue of where these initial fluctuations came from. So gravity makes things worse, but the starting point, we had no clue. And so the next of my paradigm shifts is shown on this slide. So this is important because the first of the paradigm shifts, the discovery of the cosmic microwave background radiation, was a serendipitous experimental discovery. This next thing is a theoretical development. So just pure theory. So, and it's the idea of cosmic inflation, that at very early times, the universe became dominated, the energy density of the universe became dominated with stuff which had a negative pressure. So the pressure is minus the density. And in that situation, the universe, the space itself expands faster than the speed of light. And so you can start off with a little, quantum patch of the universe, and then it expands by many, many orders of magnitude, and you can produce the entire observable universe. Not only the entire observable universe, but you can create, 100 orders of magnitude bigger universe than what we can actually see. So that's the idea of inflation. And it's a theoretical idea that, it was, this came about because of developments in quantum field theory, that if you have a scalar field that dominates the energy density of the universe, then it will have this strange equation of state with a negative pressure. Now, this idea of a cosmic inflationary phase in the early universe, it has certain predictions. It predicts that any spatial curvature in the universe is diluted by the rapid expansion. So the universe should be spatially flat. The geometry should be spatially flat. But the more important prediction is that if you have quantum fluctuations, they get stretched in scale as the universe inflates and becomes classical fluctuations that then grow under the action of gravity to make all of the stuff that we see in the universe today. So it's the generation of fluctuations that is the most important prediction from this theory. And so this meeting in Cambridge, this is the most important scientific meeting that I've ever participated in. It was held in Cambridge. Before the meeting, various people had realized that in an inflationary universe, you could stretch out these quantum fluctuations, but there were differences in people's predictions of the amplitude of those fluctuations. So people like Stephen had realized that in an inflationary universe, you could stretch out these quantum fluctuations, an effect like this, but he found, he was arguing that the amplitude of the fluctuations was so big that the theory couldn't explain what we actually see in the universe today. So the amplitude of the fluctuations was too big. There were other people who were doing equivalent calculations that were saying it's a very important mechanism, but it fails by many orders of magnitude to explain the sort of fluctuations that we need to understand structure formation in the universe today. So there was these big differences in the predictions of these calculations at the start of this workshop. Well, this workshop was only a few weeks. By the end of it, people had realized that there were various inconsistencies in the calculations and resolved those inconsistencies, and we ended up with the modern theory of the generation of fluctuations in an inflationary phase. So by the end of this meeting, we had a theory of how the fluctuations in the universe originated. It was a really big deal. Okay, so this is me and my colleague Dick Bond. Now that we had a theory for the origin of the fluctuations, we could make predictions of what we would see in the cosmic microwave background radiation. These little ripples of space-time generated during inflation would cause little temperature differences in the background radiation. And these could be, in principle, measured. And so these show some of our predictions. So this is the most technical diagram that I'm going to show in this talk. This axis here tells you the amplitude of the fluctuations in the microwave background radiation in microkelvin squared. So the RMS fluctuation is the square root of this number as a function of the multipole, which is the inverse angular scale of the fluctuation. And so what we were predicting was that you would see these peak-like structures, and this corresponds to a scale of about 2 degrees on the sky, and that tells you the maximum distance that a sound wave could have traveled from the beginning of the Big Bang till the time when the radiation cools enough that that protons and electrons can combine to make hydrogen. So that's the epoch of recombination. And then the fluctuations on these large angular scales, they are exactly the fluctuations that were generated during the inflationary phase. Okay, so those are the predictions. And to sort of put it into context, I will use my prop. Okay, at the end of inflation, so here is an orange. Okay, at the end of inflation, all of the observable, everything that you observe in the universe, all the galaxies that the Hubble Space Telescope sees, and so on, the entire content of our observable universe would have fitted into a volume about the size of this orange, or maybe a bit smaller, depending on where you put 2 pi's and so on. So you could have held the universe in your hand. So that, and so, if we can measure this stuff, if we can observe this, then we're probing physics, we're testing physics at those very, very early times. So the question is, can you actually do that? So here is a picture of, the other thing that I should mention is that there are curves labeled S. Those are the fluctuations that make structure in the universe like galaxies. These models can also predict gravitational waves. So gravitational waves generated during this inflationary phase, they can produce an observable signature as well. Okay? And then this is a simulation of a 10 by 10 degree patch of sky, showing you the sort of patterns that you could, in principle, measure. So we were doing these calculations in 1984, and back then, the no fluctuations in the cosmic microwave background had been yet detected. So then the other thing was that we could go back to doing those sort of calculations of the formation of structure, but now we had a good idea of what the interesting initial conditions should look like. So this is me and my collaborators, Mark Davis, Simon White, Carlos Frank. We became known as the Gang of Four. And you can see I was thin once. And I was also the odd one out, okay, because I was the only one who didn't have a moustache. So we had now an idea of the initial conditions of fluctuations expected from inflation. And then what we could do is we could study the matter content. If you have these fluctuations and you have just ordinary material, like baryonic material that we're made of, you could study what would happen in an expanding universe. But you could also experiment with ideas of dark matter, where most of the matter in the universe was composed of some weakly interacting particle. And that's what we did. So we started studying cold dark matter, a cold dark matter dominated universe. If you tried to make a model of structure formation just with ordinary matter, it just doesn't work. So you had to change the matter content of the universe to get anything that looked like the present-day universe. So this shows an example of a simulation that we did, back in the mid-1980s, in which we started exploring the consequences of a cold dark matter-dominated universe. Now, in what follows, I'm going to show you some omegas, and the omega is the density of a component of the universe divided by the density of an Einstein-de Sitter universe. And the Einstein-de Sitter universe is important because in that universe, the geometry is spatially flat in the absence of a cosmological constant. So omega is just a ratio of the density of the universe to the critical density. And if the universe has a critical density, then it's equivalent to having one proton per meter cubed. Okay? So in fact, we know that the ordinary material, the baryonic material, contributes only about 5% of the critical density. Okay, so in this type of model of cold dark matter dominated universe, the structure that you see on large scales depends on the density of the cold dark matter. But we had no observations back then to test the theory on large scales. So I started a project with my students in Cambridge to construct a big galaxy catalogue, and the idea was, let's construct this big galaxy catalogue and test this new theory. Okay, so this is the catalogue that we created, 4.5 million galaxies in this picture. But it didn't work. Okay, so We put a lot of effort into it, but it did not work, to verify this new theory with cold dark matter. So we wrote this paper, and what we said was that actually we could make the theory work if, in addition to cold dark matter, there was a contribution from something else contributing to the omegas, and we'll see. So we said that, that we could make the theory work to produce a spatially flat universe and explain our observations. We had to have about 80% of the mass density of the universe in the form of a dark energy. Okay, so in this paper we invoked a cosmological constant, and a cosmological constant Einstein introduced, to try and make static models of the universe. What it corresponds to is the energy density of the vacuum. So if you have empty space, it can have an energy density, and that's the energy density of the vacuum. And then as the universe expands, that energy density stays constant. So it's quite a dramatic proposal. And then here's the evidence for why, because this diagram here shows the clustering as a function of angle. Okay, so this shows you the clustering at large scales. And the shape here depends on the parameter combination of omega in matter times the Hubble parameter in units of 100 kilometers per second per megaparsec. And so our observations showed that this gamma parameter was somewhere around 0.2, and the Hubble constant is, we think it's about 70 or so kilometers per second per megaparsec. And so you can't match these observations with a universe which does not have most of its energy density in the form of dark energy. So that was the experimental evidence. Okay, so this is Margaret Thatcher. And so, why have I got Margaret Thatcher in a science talk? Well, so this was back in 1990, and Margaret Thatcher had a science day every year in which she invited young scientists, and I was young back then, to come and talk about new developments. So I went along in 1990 and presented this evidence for, the existence of an additional component, dark energy, that dominates the energy density of the universe. And she resigned 6 weeks later. And so what I think happened was that she thought, well, if the universe is that ugly, I just can't go on, okay? So this is explaining now why the universe is, with a cosmological constant, is really quite ugly. So these are some slides that I drew at around this time, and this shows, why a universe. So this is without a cosmological constant, no dark energy. Okay. So if the energy density is enough, so that omega equals 1, then omega equals 1, it stays 1 at all times. Okay, so an omega equals 1, an Einstein de Sitter universe with a critical density is scale-free in time. Omega is 1 at all times. If we have a slightly less, smaller density than the critical density, then we have to explain why the universe, has omega slightly different from 1 at the present time. We have to introduce a scale. And this is a very difficult problem because if you go back in time, omega 1 is what we mathematically call an early time attractor. The further back you go, the closer and closer to 1 you have to be. And if we extrapolate back to the quantum gravity epoch, to get an omega, say, of 0.2 at the present day, omega must be equal to 1, but deviate from 1 by 1 part in 10 to the 60. So you have to put this small, tiny number in at very early times to get a departure from omega equals 1 today. So this is why universes with low matter density were really, really always considered very unattractive by theorists, and that omega equals 1 was a much more sensible universe. But now I'm saying, well, we have to have dark energy. Well, if we have dark energy, the problem comes back again. So it's as unattractive. So now, you see, what I've got to explain is why is the energy density of the vacuum only becoming dynamically significant now? At early times, it was completely negligible compared to the matter density, because as we go back in time, the matter density gets bigger and bigger as we go back in time, but the energy density of the vacuum stays constant. In this case, the degree of fine-tuning is much worse. If we extrapolate back to the Planck time, back to the epoch where quantum gravitational effects are important, then to get a universe with a significant energy density in dark energy at the present, you have to be fine-tuned to 1 part in 10 to the 120. So it's enormous fine-tuning. Okay? And to this day, nobody understands how that can be. We have no theory to explain that. So, so that was, what we were led to from, observational arguments about structure formation back in 1990, and the general view of the community at that time was that, well, to appeal to a cosmological constant, to vacuum energy density, well, that's what scoundrels do, right? So it wasn't very well received. Now, the next of the important paradigm shifts comes in 1992, and this is the COBE satellite. So the NASA COBE satellite was launched in 1989, and it had two main instruments. So this instrument, FIRAS, measured the spectrum of the cosmic microwave background to incredible precision. And then the other instrument that I'll talk about is the differential microwave radiometer, and that measured the temperature differences in the cosmic microwave background. And so the DMR instrument produced this map. And so this satellite discovered temperature fluctuations in the cosmic microwave background, and the amplitude of these fluctuations is 1 part in 10 to the 5. Okay? So very small fluctuations, and this shows the map that came out of the COBE satellite. Now, the significance of this, it detected these fluctuations which we thought should be there. But now consider the following. The angular resolution of COBE was about 7 degrees. And what you can see in this picture is you can see correlated structures that are correlated on much larger scales than 7 degrees. But the distance that light could have traveled from the beginning of the universe to the time at which these photons come towards us, that subtends an angle of about 2 degrees, corresponding to that first peak in the spectrum, the power spectrum of the microwave background that I showed you. So anything larger than 2 degrees was not in causal contact at the time that the photons were emitted to make this picture. So in other words, this fluctuation here, okay, this side is not in causal contact with that side. So this shows you a picture of material which required physics that apparently violates causality. But that's explained by the theory of inflation. So the fact that you see this picture, that gives very, very strong evidence to something like an inflationary phase of the early universe to explain the correlated structure that's seen in that map. So this shows the 2 PIs of the main instruments. George Smoot, who was PI of the differential microwave radiometer, and John Mather, who was PI of the FIRAS instrument, and they won the Nobel Prize in 2006. So, and George Smoot caused a lot of controversy at the time because he said, that he gave a press conference where he said, this discovery, this map, was looking like the face of God. You see, so never mention God in a press conference. Okay. So that's the next of my paradigm shifts, okay, the discovery of the fluctuations in the cosmic microwave background. Then, in 1997, the next of the paradigm shifts was the discovery of evidence for dark energy. So this came in 1998, and it came from surveys designed to find distant supernovae. So these are 3 galaxies observed with the Hubble Space Telescope, and then what's shown are the images after a supernova goes off. They're easy to spot. You just look at the pictures and find where the arrows are. Okay. But supernovae, they're almost the same luminosity. So they're like standard candles. And so if you observe these supernovae at different distances, then you can get a test of the geometry of the universe. And that geometry tells you about the matter content. And so these were the first results. So it shows you the omega in in the omega in matter, including dark matter, and then the omega in a cosmological constant. Spatially flat universe has to sit on this line here, and these were the results. And so for a spatially flat universe, you had to be dominated, about 80% or more of the energy density had to be in the form of dark energy. And that's a geometrical test. Okay, and so from 1998 onwards, the community accepted that there was this dark energy, and then the people responsible, so Saul Perlmutter, who led a group from Berkeley, and then this is Adam Rees and Brian Schmidt, who they led a group based at Harvard that led to this discovery. So the picture now is building up. You have Big Bang origin, inflation to generate the fluctuations, the cosmic microwave background anisotropies as evidence of supporting inflation, and then the geometrical evidence from supernovae that tell you that the universe is dominated by dark energy. So those are the main pillars. Okay? Now, we've been fortunate in cosmology in that each decade we've had a major satellite experiment dedicated to measuring the anisotropies in the cosmic microwave background. COBE, so this is my historical analysis of research into cosmic microwave background. First, we had the COBE satellite, 1992, for the discovery of the cosmic microwave background fluctuations. Then the NASA WMAP satellite that was launched in 2001 and reported its first results in 2003. And then the Planck satellite, which occupied many years of my life, that was launched in 2009 and reported its first results in 2013. So we've built up a picture of the cosmic microwave background, fluctuations on the sky. This is the picture from the COBE satellite. This is how it looked to WMAP and then to Planck. So remarkable improvement in precision and angular resolution. And so with this map, we can compute the spectrum, so the amplitude of the fluctuations as a function of scale, to compare with those theoretical plots that we made back in the 1980s. And this is what we get. So the blue points here are the results from Planck. So this is basically giving you the mean square amplitude of the fluctuations as a function of angular scale. So here's the angle in degrees, but then expressed as multipoles down below. So the basic structure is you see oscillations caused by sound waves when the universe was highly ionized. And then these fluctuations on large angular scales are basically as they were when they were generated during the inflationary phase, when everything was this size. Okay? So it's pretty remarkable that you can actually do this. So the blue points, the individual measurements, multipole by multipole, shown by these little dots, and then I've averaged them to show you the blue points. And then you can't really see the errors anymore. The precision is so great. So on the bottom, I've shown the residuals with respect to the best fit. And the best fit is an inflationary model, inflation in a universe that's dominated by cold dark matter and dark energy. So the fit is absolutely brilliant, and it's very rare in physics that you get agreement between theory and observation at that level. So the evidence that this theory, despite the fact that the ingredients seem bizarre, okay, is actually a description of nature, I think is very, very strong. Now, when COBE discovered the fluctuations, George Smoot said that it was like looking at the face of God. And I think now that we have the Planck measurements, that this is wrong. Okay? So I've made this little video, okay, to show you why I think he's wrong. Okay, so if I play the little video. Now, what that means, I don't know. But I find it a bit disturbing that the fluctuations in the cosmic microwave backgrounds are imprinted in that profile, okay? So, anyway, we can learn a lot of stuff from measurements at that precision. So here's what we think is the composition of the universe to high precision. So ordinary material, the ordinary baryonic material that we know about, makes up only 5% of the total energy density. Then the dark matter makes up 27%, and then 70% or so is dark energy. And you can't change these numbers by very much to maintain that fit to the spectrum. Okay, so here's the map. In fact, it turns out that my colleague in Cambridge, Martin Rees, knew it all along, okay, and he wrote this book called Just Six Numbers, and we can explain, the observations of the cosmic microwave background in just 6 numbers. Not quite the same numbers as Martin thought, but the basic idea was right. So now, to go back to the title of the talk, do we have a standard model of cosmology? Well, the answer is, I think, is clearly yes. But inflation is a very pretty theory, but we don't understand where it comes from. So we can't tell you very much about the particle physics that caused an inflationary phase. So it's not understood. The dark matter, we know it's there, but we don't know what it is. So it's not understood. The nature of the dark matter is not understood. Some weakly interacting particle, but we don't know what it is. And then the dark energy is even worse. We have really no understanding at all about dark energy. And as I said, that to explain what we see, we need fine-tunings at the level of 10 to the 120 that nobody has a clue. So, is this model, of lambda plus cold dark matter, is it just a fitting function? Have we invented loads of epicycles and unusual things to explain the data? And I think that the agreement between that model and really precise observations of the cosmic microwave background argues against that. There must be some degree of truth to this model. So I just now want to summarize about, what I've told you in this talk. Here are the paradigm shifts. 1965, discovery of the cosmic microwave background radiation, when I was 10 years old. Inflation, the quantum origin of fluctuations, really important theoretical discovery, when I was 27. Discovery of CMB anisotropies when I was 37. Discovery of dark energy when I was 43. And then nothing in the last 27 years. So if you'd started your PhD in 1998, which was when the supernovae evidence for dark energy was published, then you would be nearly 50 now. And you've never experienced a paradigm shift. I was really lucky in my career because we went through this revolution in understanding. So where do we go from here? Here is our theory. Okay, so an inflationary phase, cosmic microwave background, and then the first stars and so on form afterwards. If we were to be able to detect gravitational waves, I showed you that you could calculate the effect of gravitational waves generated during this inflationary epoch on the cosmic microwave background, then you'd be able to see right back through gravitational waves to the inflationary phase. We haven't detected anything like that yet, okay? And if we were to detect it, it would be the first time that we would have ever seen a quantum gravitational effect. So that's an important target. But what we've learned about inflation is really odd. Okay, inflation, once it starts, it never ends. So inflation is eternal. So this shows you, a background that's inflating, And then every now and again, inflation ends and you get universes which may have very different properties. Okay? So we're just in one little pocket of this multiverse. Okay? Now, I actually call these things exo-universes, you know, and that's to annoy my colleagues in Cambridge that work on exoplanets. Okay? So I say, you know, I'm working on exo-universes. It's much cooler than exoplanets. So there was a while at least when, you know, this multiverse idea, people thought, well, you know, there's interesting things that we can do with this, because if we combine, you know, the inflationary, you know, this inflationary multiverse with string theory, then, you know, string theory, you have 9 or 10 spatial dimensions in addition, you know, some more spatial dimensions than the 3 that we're familiar with. And you have to get rid of the other dimensions by compactifying them, by making them so small that we don't experience them. And so the geometry, the way that you can compactify these dimensions, you can do it in very different ways. And so the different ways in which you compactify these dimensions correspond to different physical laws at low energies. So the idea was that, well, you know, you have, you know, multiverses, you know, multiverse, and you have different laws of physics in all of these universes that condense out of the multiverse, and that maybe the reason that our universe is so fine-tuned and special to make life. So, for example, the 10 to the 120 fine-tuning of the dark energy is just chance. Okay, so here's the idea that, you know, we have loads of Buzz Lightyears here. We pop them into different pocket universes that emerge from this multiverse. And in practically all of them, they get frazzled. But then there's a very rare chance that they're in some universe that has the conditions to allow Buzz Lightyears to survive. Okay, so that's the anthropic principle. And, you know, so, you know, relying on the cosmological constant or dark energy to get you out of a hole is, you know, something that is regarded as, you know, the work of scoundrels. The anthropic principle is even worse. Okay, so, but the problem is that we have no understanding of how to calculate relative probabilities in a multiverse. This is a very deep problem in, you know, in cosmology. That you know, we just don't know how to define a measure on this multiverse. So general relativity is a local theory, so it can't tell you how to time slice in this multiverse. So this is an attractive idea, but it has, at the present, it has no predictive power. The other thing is that it's not just that it doesn't have predictive power, but we've really got ourselves into a mess with the multiverse because you know, we end up with an infinite number of universes, some of which are infinite. So it's a really serious problem. It's so serious that what we've learned about inflation has led to, you know, serious scientists. This is from a Scientific American article by Elias Steinhardt and Avi Loeb, that basically say that, you know, these problems are so serious we have to abandon inflation. So, so cosmology, you know, we've developed this theory. It explains observations, but it raises really difficult conceptual problems. So where is the next paradigm shift likely to come from? So one possibility is theory. So So the conceptual problems raised by eternal inflation are really serious theoretical problems. And they are as serious as the problems of classical physics before the discovery of quantum mechanics. So we need a revolutionary new theory. This is absolutely essential. We will need a big change in our understanding of physics to solve these discrepancies. So where will it come from? It could come from, tomorrow, from a new young Einstein who has brilliant ideas. But you can't bank on it. But we definitely, eventually, will need it to understand these problems. So the question is, theory may be the next paradigm shift, but it may need some additional pointers, some additional observational developments to point us in the right direction of a theory. So the theory has some issues that are not understood. For example, the Hubble constant that we get, the expansion rate of the universe, that we determine from the cosmic microwave background, doesn't agree with what observers measure from the local universe. So that's known as the Hubble tension and is unresolved. Another problem is from gravitational lensing measurements that seem to suggest that the amplitude of structure in the present-day universe was lower than we would infer from the cosmic microwave background radiation. But I think that the evidence for that now is, my colleague Alex Salmon and I proposed that this was caused by the effects of stellar and active galactic nuclei pushing material around in the universe, and the evidence for that is building up. So I don't think that's a problem. But looking for areas where the theory doesn't work, the question is it data or is it new physics? So it's possible that we can learn something from discrepancies. We don't know very much about neutrinos, so this is completely feasible that we can learn about the properties of neutrinos from observations, of cosmological observations. And then the gravitational waves, as I said, if you can detect that, you basically proved that inflation happened, and you fix the energy scale of inflation. But we don't know whether it's possible to do that. Okay, it's very easy to construct a theory in which the gravitational wave amplitude is orders of magnitude below any possible detection limit. The fluctuations, as far as we know, obey very simple statistical properties. So they obey Gaussian statistics. And it depends, on whatever drives inflation. If it interacts with itself or with other fields, then we could get deviations from Gaussian statistics. They haven't been detected yet, and they may be impossible to detect. And then there's the dark matter. Can we detect the dark matter in a laboratory or from the Large Hadron Collider? And that would be my bet for the next paradigm shift. It's the best bet. So is the legacy of the Planck satellite that I worked on for 20 years, is it the lambda CDM cosmology all the way down? Well, it could be. I mean, we could, so that could be the legacy. However, there are lots of projects, big projects, and this is something that amazes me, because you think that governments would be more interested in making sure that the trains run on time and things like that. But governments of all political persuasions have an unusual interest in dark energy. And so they funded large projects. Here's just a selection. This is the James Webb Space Telescope. This is the Dark Energy Spectroscopic Instrument. This is the Rubin Survey Telescope, and so on. So there are a lot of projects, square kilometre array, and so on, designed to test the cosmology and the nature of dark energy. So, what I'm hopeful is that in, say, 2080, there's somebody giving one of these talks, and what she will say is, well, you know, when I was 3 years old, you know, dark matter was not understood, inflation was not understood, dark energy was not understood. In fact, cosmology back then was little more than a branch of the philosophy of science, you know? And so to the young people, I wish you well in the quest. So,